Welcome everyone for Cloud Computing and Big Data. Today we have our lecture 4 on virtualization and scalable data center design. So today we're going to review some of the basics of virtualization, which should be in the pocket of every computer scientist or computer engineer these days, and is surely also taught, I think, in one of the introductory courses in the university. So we keep it very brief with a view really how virtualization fueled cloud computing, how it enabled essentially multi-user, multi-tenant data centers, and so on. But before we go into the material of today, let us review what we had the last time. The last time was really formalizing a little bit machine learning with the aim, of course, of using it in cloud applications, but to get a better understanding of all the different mathematical building blocks, right? Where you maybe are a little bit confused if you don't had a proper machine learning course before. There are many, many different wordings, training examples, learning algorithm, the hypothesis set, final hypothesis, etc., etc. So the last time we tried to blend this a little bit with one practical application, the violations in a restaurant in terms of cleanliness or, lots of violations of the food inspection gives you an indicator if the food inspection will pass or fail. So we thought about it as a binary classification problem. You have that here, fail and pass. So we looked in the data and we transformed the data, did some data preparation. Also, if you remember, there were actually 5 classes, but we merged them more or less in 2. Also learned a little bit about class imbalance. However, long story short, we had this binary classification problem. So this is now the idea, the business understanding, what we want to achieve with the data set. And we were very lucky. We had the supervised learning example. So it means for every of the input we have about the restaurants, we have also then the results, which was then pass or fail, or as I said, transformed from 5 classes into these 2. So that is an important part leading into data inspection, then understanding what data I have, refine the business understanding. And now, when we start with machine learning, one of the most key elements is a training examples, right? So this is something that we must have, right? And this could be, of course, huge demand for storage. Hence, we go for cloud computing, which was one part of review of the lecture 3 as well. If you think in the beginning, right, when we talked about greenfish, for example, and using the Copernicus marine data sets with terabytes and gigabytes. So this is something where you quickly end up on high performance computing resources or cloud computing resources. That's where it starts. If you remember, we picked a little bit one part out of the overall data called the training sets. That's where we train the modeling on, which we basically give a first place as an input to a learning algorithm. But before we go there, we also have to think about that, we have to pick some specific hypothesis set out of our skill set. What does it mean? It means like we are having a lot of machine learning models at our disposal. Right? You see here, for instance, support vector machines. You have essentially logistic regression. That's the one we wanted to pick because we have a binary classification problem, relatively simple. So no need maybe to go to support vector machines nor to artificial neural networks that you see here. That could be another hypothesis. So each of those with trained weights, like logistic regression here, you say the weights for the input summed up linearly and then, having the logistic function, etc., etc. This weights changes means also another hypothesis. Hence, we have more or less infinite amount of those in the hypothesis set, but we want to pick one G out of this. This should be then our final hypothesis approximates F very well. So F was in our idea initially an unknown, let's say, target function mapping, from the space X to Y. But here you see it's an unknown target distribution because learning is basically not possible with function approximation because sometimes in the data set you would have, for instance, the supervised one or whatever, you would have something which breaks a function, right? And we had the example of movie rating. If the same X goes in and you like the movie and say, yes, it's a perfect movie, but the same person looks at 2 years later and then suddenly says, no, this movie is not anymore interesting. So this is not a function, hence we have a probability assumption around it, model it with noise, P of y given x, and this brings us then to this probability distribution that in a way, we assume that these training examples that have been created from a target function or an ideal function that some people say, that actually not really exists, right? But we basically assume there's something there in nature that had created this. And the probability distribution is basically to the rescue. It also stands for a so-called PAAS statement partly, saying probability approximately correct learning, so that we assume the training examples come out of the same probability distribution. So when you have Netflix ratings, you look on this, you work on this, you don't go maybe to a bakery rating, right? So this is different probability distributions, different elements, and maybe even attributes. But the attributes can be the same. Important is that the probability distribution is, assumed to be the same. Then for the formalization, it's very clear to say that our vector X, with all the attributes we have about some certain person, about some certain bakery or movie, these are the constants in learning. So that's the interesting thing for us. That's the data given to us. Hence, they're constant. All we do, like you see here in the basically hypothesis about the logistic regression, we change the weights with a learning algorithm. And that's where we come now to the lower part here, right? Where we think about that the learning algorithm always goes together with a certain, model you pick. Support vector machines, you use quadratic programming. In artificial neural networks, you have heard from Andreas Lintermann, you use backpropagation of error through the layers. And logistic regression has now an error function that we define here that helps us a little bit, with optimization, as we had said the last time, to iteratively solve, this problem going closer and closer by minimizing the error measure. So it's an optimization problem by picking the right W's, taking gradients, which is computation expensive, if you remember, to, in a way, going, time after time with this iteration to the hopefully lowest error that we have. Then that is what we added also to the error measure. And this is also something we have, to see if we're getting better in learning. And this could be also very application specific, right? So the error measure should fit a little bit to your application problem. But in a way, you have all learned this now, and let's make the bridge then why we basically do this also in cloud computing. We see that the Apache Spark is basically supporting this very well, and also in a production sense for, industry projects and so on, with pipelines. And the pipeline idea was essentially that you basically train a model with this idea of the learning algorithm. You have then the same steps for working on the data. If you remember, the violations were text, raw text. Then we go to words, then we have a feature vector, and this tells us probably a lot, like dirty, clean, these indicators of some famous words you would say that are in the violations or basically not in the violations. So basically giving us a positive feedback about restaurants. This is something very important for the classifier here that we want to have in the binary classification. So the feature vector then is working with these W's that we give in, right? This input with the W's to make these more and more correct using the error function and coming out with a logistic regression model, this red thing here, right? So now this is, with this algorithm created and created the blue model. Sorry, this is the algorithm. This is logistic regression model that comes out. And then, we have seen this is scalable even with Spark, right? So we can add more worker nodes or less, depending on the amount of data we have or on the complexity of the computing we want. So if you have more data, more complicated modeling, we maybe want to go to artificial neural networks. Here you go. You need probably much more worker nodes, maybe even GPUs attached to it. So in the same idea of the pipeline, and then we end the review, I think it's still very important here to understand, this aspect. We can now take this logistic regression model and give it to the same idea of the pipeline using the, tokenizer words hashing function. But of course, here we don't train anymore. This is now the testing phase. Hence, we use a test set, the other part of the data set we didn't touch, and then, fit with the labeled data and understand really, if our model works well, basically with unseen data. So again, this one slide might be a sort of crash course for machine learning as a whole, especially in the supervised learning setup, right? So hence, for those that are really seriously interested, you need to learn a bit more about machine learning. Each of these mathematical building blocks is a bit loaded. So how I pick, the training set and test set, the ratio, maybe 80% training, 20% test, or 60%, 40%. This is all not obvious, and machine learning courses help you. What we left out is a bit regularization, validation, right? These are things that should be also in the pocket to combat overfitting of machine learning models. Also something I don't really touch. So there's lots of these things, behind this mathematical building blocks, learning algorithm, and so on, so that learning is just feasible in a probabilistic sense, giving the, probabilistic distribution and other elements, coming back to Hoeffding's inequality, and then so on and so on. However, we made the case for Apache. We have seen it was very nicely supported, but we basically jumped ahead a bit with practical topics to get you now to the final assignment essentially here in the course. And that's why we put it a bit earlier, but we left out a little bit why data centers now can scale, also in a way, in a physical sense, right? So how does it work? We need physical data centers with lots of, resources, and why I can add and remove so quickly. And there's virtualization to the rescue, and that's what we talk about today. So this is a little bit intertwined, but as I said also earlier, virtualization is something which is so basic. I will just highlight here very important concepts which are sort of, pointing us to the idea why cloud data centers need virtualization, why it is basically today a necessary ingredient of having so-called virtualized service in contrast to the physical servers. And we will go to some terminologies really, like virtual machines, virtual machine images, instances. What are the difference of those? Because this is also very nicely supported in almost all cloud computing offers today. So we'll look a little bit on MS Azure, but you find the same idea of this virtual appliances, images, instances, also in AWS and Google Cloud. So this is pretty basic. Then, when we come to the cloud data center design, we take some of these aspects in the second part today, and we'll look on a broader scale, really, to think about, okay, how we have the idea of having multiple data centers, what happens with, metrics in this, failures, how we actually go with the idea that, all of this is generating a lot of heat to put these big data centers. So we need some cooling. I'm certain you have heard about this, especially in Iceland. Here we have ambient air cooling, which is quite good. And we will look in this a little bit with Icelandic data centers as well. So then let's go to the virtualization technology and look a little bit about what you maybe already know from other courses, but we review here some of the terminology to put it in the context of cloud computing. And we start here with a slide which really shows you nicely an evolution over time for cloud computing, right? So, but 20 years ago when I'm starting, lots of things, were very different. There were no computational clouds. So we had high throughput computing systems, some pizza boxes, as people would say, smaller computing powers that have been, put together doing, let's say, P2P networks and so on. On the other side, we had already some of these costly HPC machines, but not at all with GPUs and not at all at the scale we have today, 20 years later. So this is high performance computing systems. At that time, still, they were already quite powerful number crunchers, put together in clusters, and were more or less really centralized. You had really one data center or computing center that hosts this HPC machine, while the P2P network, the idea of having really more distributed control and really geographically, basically dispersed and everywhere put together. And this was also the coin of the idea. By having more and more of the HPC systems around, in different geolocations, but also having this P2P networks, we really, in also different geolocations. The idea was born also closely related to CERN, basically to the Large Hadron Collider, searching for the Higgs boson, for physical, let's say, phenomena. The idea was to put computing together in a way worldwide, which was a worldwide Large Hadron Collider grid, and so on. And we had in previous lectures, we had still some lectures on it. if you go back in the history, in the YouTube, or if you look about it, grid computing was a big hype 10 years, maybe 15 years ago. And this is something where this was a birth, in a sense, of the foundations of the internet clouds you had today. So what was missing there still was the big bold virtualization. So VMware just was starting, virtualization was not commonly operated. It was, here and there lacking performance. So, I mean, you have a virtualization layer we will explore very soon on top of these resources. So this took away performance. But nowadays, these technology has been so much advanced. And this is why we also will review virtualization today, because essentially the grid computing was already cloud computing, but with added virtualization and industry interest, if I may say so, this was really thriving. And maybe along with it, you would have the Web 2.0 services, the service-oriented architectures. You remember, maybe some of you, web services, SOAP. There was not even REST at that time. So REST is also relatively new, the representational state transfers. At the same time, more and more other sensors came in, integrated into grid computing, but also nowadays in clouds and many of these things. So to sum up, you would say without virtualization, there would be also no really cloud computing today. And we want to explore why is that the case. And obviously, if you want to read more, you see that AWS and others here, MS Azure, and whatever cloud provider there is, they usually also talk a lot about virtualization and have, their clusters virtualized. So from the concepts perspective, I think, again, very quickly, because I think that is sort of basic computer science, which many of you should already know. You have a traditional computer with lots of hardware, physical hardware, that's now important to understand. And you would have a host operating system, some Linux derivative, Windows, and within it, there are different applications that will be run. And basically, the host operating system has full control over the hardware, right? So reading from disks and, et cetera, et cetera. So after virtualization, you see that is a little bit different. So you have still, of course, physical hardware. Without physical hardware, nothing would work. Even not cloud computing would work, right? So there's no chance. Clouds appear virtual and is nice and somewhere, but in some point in time, even a cloud needs physical resources, some hardware somewhere in a data center running to basically have all these applications, Spotify's, whatever we have in terms of apps, all the mobile phones these days also support it. You've heard from the recent incident, perhaps, that, Spotify was not reachable, because there was a problem in one of the data centers from these providers. I will not go into details, but you see then quickly that these errors will materialize, and then the whole service is not reachable anymore because you need the hardware. Now, virtualization helps us still to get quickly, on track again if there's an error, and we will explore that in a minute. But let us just think about now how this virtualization layer that you introduce there, on top of the hardware, now changes a bit the picture. So you would have a virtualized set of hardware that you share with different, let's say, potential guest operating systems, which means you could have a Linux derivative, you could have, Windows in parallel, and some of you may even have that on your laptop here. And then, serve different applications. And this is a concept we are known as virtual machines, right? You can fire them up, you can stop them, but gives you much more flexibility on your own little hardware if it is a, let's say, traditional computer or laptop, whatever. So this is still very nice. It gives you quite flexibility. And for us, it's also a better system efficiency that we can get out there. And that is something what we want to explore, especially when we go to the larger scale. Hence, when we revise this a little bit, you have here this physical machine with the hardware, and you have this operating system and the application we just explored. And what we now have to see is like when you have this native VM space, that, this is another wording we should just, remember a little bit, that you would have so-called privileges that, this hypervisor can do now with the hardware that the operating system cannot do anymore. Again, I think it's important to understand that the operating system has full control on the physical machine, on the hardware, given the operating system is, just on top of the hypervisor. Basically, you leave a little bit this, privileged space to access the hardware how you like it, right? Though hence this bare metal, bare hardware is a little bit virtualized in this guest operating system, and you potentially share it with many others to have your guest operations application supported. And this is sort of is an important concept here that is also reaching into, security in a way to not control the hardware with any, non-privileged users in space of this, basically virtual machines. And the different ways how you could, model this, and in a way, I think that's not so important to always, have this in your head now with the different layers. But it's important to understand that, it's a big difference between having the operating system on the physical machine hardware or basically having this abstraction layer, right? And that this abstraction layer is really something that, of course, can be put to different layers in a way inside this stack that you see on the right side, right? So this virtualization is here very closely on top of the hardware, but you find in real virtualization solution that some people have really done this in different, parts of it. Now, for us, when we have now this virtual machine manager, right, which does this abstraction for the guest operating system, that enables us, of course, something quite nice, so that we are basically independent of an operating system. We are independent of the applications. So with hosting then this VMs or multiple VMs that are isolated from each other, you can add more and more if, for instance, the hardware is not, utilized enough. And this pinpoints us already to something called multi-user, right? In the moment you're very much focusing, thinking, that's my laptop, no one else is about to touch it, which is of course understandable. But when we move to data centers, then of course we want to support many, many different users at the same time with the same hardware. And this is something where really sort of is a breakthrough now, right? With this kind of virtual machine layer and the abstraction. Because through this, you can really increase the server utilization, being totally safe because everybody has its own VM, right? And all the users have different VMs. And, this is something where you see here one claim from VMware, for instance, one of the providers, where you can, increase the server utilization instead of 5 to 15% to 60 to 80%. If you have a normal server. Now, if you do this in a bigger scale in a data center, you can imagine how the weight of these percentages are. So hence, this was really fueling now the idea of thinking, okay, when I have virtualization, I can actually share this much more. But there were other factors that also then, basically coined really the breakthrough for VMs within the data centers without the large servers. And this is the interesting idea of what you can do then now suddenly when you are working in the VM space. And this was before not really, used a lot when you have just, a plain operating system on top. Here you see one of the things we just discussed. Multiplexed VMs is a word for it. You would say many different applications with different operating systems can use one virtual machine manager. And then, you can even, access the same storage. And you have another, idea of combining this potentially then with a data center, with other hardware, another rack, etc., etc. So this idea of sharing the same hardware with different applications. And here I already put to you now this different users. This is a key concept, right, for the data centers. Not at all at the order of scale, right? Here we have to think about data centers have thousands of users. So you need much more hardware, but still basically the concept is the same. The interesting thing what VMs give you is also this instances of a VM that you can actually just suspend and store, right? Status of the operating system of the application can be completely, as it is completely virtualized, stored to disk and reactivated. So you see this in C is a basically counterpart, enabling also porting, which is a bit hidden here, right? So you can port it potentially to another hardware system because you have anyway the hardware virtualized with the operating system. So you do something which then alludes also to this D part, which is now a key concept when you have errors, and which is in data centers very common. So basically, data centers operate under the assumption there's always errors. Some hardware will overheat, some networking will occur, in terms of problems, and throughput and so on. And when this is failing, we have something called live migration. So during the runtime, you can even port the VMs to another hardware, which is actually operating quite nice. So all of these combined in a way enables us then to keep the uptime very high, right, for data centers. And this is important because in their SLAs, in their service level agreements, they usually state this. We have a 99.9 uptime or 99.9 or 99.6 uptime. You can review this in the recent incident that we have seen now with the networking that Spotify was not reachable and so on. And these kind of things means that, the provider is essentially, giving you a service level agreement. And, this is what they operate, and never it's 100% because errors always will happen. So nobody will give you 100% SLA usually, right? So it's always 99 point something. And you see here the time how that works in practice. I don't go to the details. I mean, this is pretty clear for those that don't really understood it yet. Please review that. But you see a little bit here how little time, 165 milliseconds total downtime, how this can work when one certain host is failing and you just live migrate to another one. Of course, this is here and there maybe idealized conditions, but still this shows you that for a user, it might be not really even, visible, the service interrupt. So then this brings us more and more to the idea when we have these various VM instances, right? Then we can maybe fine-tune this already and say, well, why should we as users get a plain, let's say, operating system without any applications? But why we cannot just bundle that already, and some of you know that. So some people of you are actually Ubuntu users, some are more the, SUSE Linux users, some actually are the Windows users. So, but, what about having, if we can store, if you remember, we can store and resume these, we can build so-called virtual appliances that basically can bundle all together the applications, the operating system, and so on and so on, and make it ready to run. And if you see here on Azure as an example, that's how it could look like, right? So you basically in Azure can just pick a virtual appliance with a virtual machine that has already installed Ubuntu servers, has already installed, SUSE Windows servers of some kind that you can then use, instantiate, and you don't need to install the operating system or even some applications with it. And this is now, of course, something where you have these images then there on storage, and you can create another one and another one out of this and create instances as you like. You can modify these images, of course, up to your, basically requirement. So maybe adding some specific applications that you want to have on your Ubuntu server and have this VM instance ready to run on a virtual machine server. Of course, you see here also this estimated monthly cost. Again, the short disclaimer, if you go to commercial cloud providers, you have to pay for the service, right? But this, of course, comes with a very high uptime. And the way you see here, it in MS Azure, it also is available in, Amazon EC2 instances. These are not obvious to you. We will see how that materialize when we talk about, lectures on infrastructure as a service and so on. And these will also have, you say, VM instances ready to run on all these different servers, and the same is in Google. Hence, this is sort of a key basics that fuels cloud computing today from the very, let's say, basic services. And for some of you who are a little bit advanced in maybe computer science now will already smell something, which brings us to a very later lecture, meaning containers. Right? So containerized applications are a little bit a competitor, if you want, to this virtualization concept in some way. And I just note that here so that some of you know we don't ignore that fact. So we will come back to, basically containerized applications and Docker and all of that and Aptena later in the course. And, it also is important because today the data center industry is going, also to this kind of aspects, but still is virtualization, of course, inherently in it, right? Many of the, instances, all of this is basically done today. So the rest of today's lecture here in this part one was just more or less a bit of a walkthrough, that some concrete, let's say, examples. Xen is very, known for being, for instance, an open source hypervisor. I was quoting VMware, so that you have some real products which are using, let's say, this kind of technology virtualization out in the field. You can go to Xen and basically see very similar concepts here that you have, that we discussed before. So you have your kind of physical hardware devices with the hypervisor or the virtual machine manager. You have now the opportunity to have different, let's say, operating systems, or as we said, guest operating systems, and then different applications hosted with it. And you will see that every of these softwares, Xen and others, apart from just being open source or commercial like VMware, they have here and there some very specific features, right? So, for instance, here we have this so-called domain 0, which is a very specific one. In other words, that there are some that are not really completely equal from the guest operating system. So could be some domain which is, let's say, still very prominent, and then doing certain aspect that the other aspects or the other, let's say, virtualizations you put here on the right side don't have. But this is very, very specific thing in Xen. I don't want to lose much more time on that. Just that you know that, of course, each of these different technologies coming also quickly to VMware, which is now by Broadcom basically acquired. So then you have different features in all of these different technologies. And of course, obviously, some of these technologies, of course, are very much also oriented to your own laptop still, to your operating system for a traditional computer. Not all of these virtualization technologies are in cloud computing today. Some of the players are, so VMware is also a big server installation and so on. And again, a bit how it works here, you see essentially here, we have discussed this already. And here it just shows you that some of these commands, normally you should always go via these layers. The guest operating system has to operate with the VMM to actually then go to the real hardware in the sort of mode of the supervisor. And with this, you basically have a way as users thinking about directly going to the hardware. There are some exceptions to this, which would be much more important to look in a virtualization, let's say, course or so. And in the end, I leave it at this, that you also understand a little bit, some concepts between full virtualization architectures and so on. So host-based virtualization architectures, just for the name of it, is a little bit an interesting aspect that some of you maybe have already also on your laptop. When you say you have your typical physical hardware we discussed before, but you would not have the virtualization layer directly, you would have a host operating system. And I know some of you do always Linux first, and then put the virtualization layer on top, and then have something like in guest operating like Linux, like Windows in it with applications, or you have your applications directly on the host operating system like Linux. So this is possible. Some people know that very well, use that concept. And this is different from para virtualization examples, for instance, where you have then essentially the traditional model that we just said, say hardware, you have a hypervisor here that is essentially then have the guest operating systems. But para virtualized already means that some of the requests directly, basically can go to the hardware. In other words, it's not simulated, it's not virtualized, which is, let's say, also something you can look up in KVM if you want. So again, something which is, very specific to the different distributions perhaps as well. It's also not so important to know these differences by heart, right? So obviously you can imagine data centers operate in a way that it fits best to the users and maybe also to the best of their profits. So in the end, from our 10,000 feet perspective, again, for us, it's important to understand that all these large data centers you see use really these virtualized resources. So, and you see again how that fuels here this hardware storage. You think it's one big cloud, but even in Amazon, you have to pick which region, Virginia or other parts, Europe and so on. So in the end, these are all looking nicely virtualized and somewhere in the cloud, but you will come back to some virtual data center somewhere, giving you all these resources, right? And this is something what is really important to understand. And in the course, you will also know we will go to one of the data centers so that you really touch metal, as I would say. Important is for you to understand the physical hardware so that we see a little bit on this. And we will do this more or less to the end of the course together. So in this is, of course, lots of management, and a huge virtualization infrastructure means also a lot of possibilities in order to fine tune for users, in order to monitor your infrastructure, and so on and so on. So there are lots of building blocks that we will also look in lecture 15 on how you do a cloud with the cloud operating systems and so on. And let's not forget the security aspects that we really don't have here, for instance, in this particular slide, which is equally important. So here's a good example of, more or less going to a really data center scale away from what you just saw with all the different laptop computer-oriented ones with the basics. But in the same way, you would say the data centers have to realize this cloud, really somewhere physical resources, right? And this basic is really not changed. All what is changed that the virtualized platforms on top of it are much more scalable, larger, and maybe also geographically distributed, not only one laptop in one room, right? So there's a big rack somewhere in Virginia, a big rack somewhere in Europe, and so on and so on, and a big data center, perhaps, even if you think about the Amazon scale and Microsoft and so on. They still operate on the concepts of different virtual solutions, could be a virtual machine with different agents and solutions, which are basically then give solutions for the customers, right? So whatever there is running it. A data center in the end knows it's important that the applications, but they also don't necessarily need to know what's running in it. But they have to do lots of management here. So the virtualized management means a lot of security, data management, resource provisioning. Where are we with the physical resources? Are they really utilized enough? And so on and so on. We will review this also in the second part of this course today, much more when we talk about data centers in depth. And with this, you basically have an infrastructure provided for your users as a data center. And this is, let's say, totally independent of what you see here on the bottom, right? The user will not necessarily know that this is a server there and here. So the whole stack basically that you have here, hence OpenStack is also one of the cloud operating systems. Talk about the big stack of services you have to create. The infrastructure service is then something where you have your users, system, basically the accounting, billing, right? Swiping the credit card is a very important concept. Mirror management, so data security, data backups, data duplication, and so on and so on. So you have to think now that this is really on an infrastructure scale in a data center. Hence, this is something where you have an order of magnitudes of scale. But when we come now then to the idea of sharing these resources, this is all what it enables, right? Because now we have this large scale. We can say this green user group gets these resources, this cluster, and then there's another red user group. These should getting these kind part of the service. So we can, have a very flexible resource sharing, and I can change this over time very quickly. And this helps us also very quickly for the live migration, right? When we have, again, a problem, an error, fault tolerance, this is all alluding already to something. And, this is also a concept then that needs to be integrated with your scheduler, right? When you think about Apache Spark cluster deployment, when we had this yarn scheduler, right? So basically, the yarn was already doing what you see here, put the jobs of different customers at different places within the cluster. And you have seen this in the Jupyter, of course, it was just for your jobs. But if you think about it, makes a step in your mind that you have in a multi-user environment, this is now for different users, and you have to do this. So it's a very relatively complex mechanism to share the cluster with so many users in a secure way, which is not only something where you need a scheduler, but where you need the whole concept of virtualization quickly, where you need, let's say, different privileges, who is allowed to do what on the hardware. And this is all fueled by essentially this virtualization concepts that we heard, and by using VMs more easily around. Now, when we now go towards this step, and again, the second part will be more of it, think about that there's this idea that you have then this large data centers, which essentially pick up the same concepts we had before, right? So we have hardware, then there's a device drivers and the I/O stack to get to the hardware, and you have device driver in the guest operating system. So this is what you would know on a lower, let's say, small scale. If you take the same concepts and putting it now to a really large, let's say, data center, you will end up like this, right? So you would have a very fragmented way of looking at it that, basically inside the data center, some are using, VM0 for a database, some are actually hosting web service. Another one is again a database, others have hosted middlewares. So the application concept that you have here and the different needs of users, which is a bit explained here, means now you have a mapping to do inside your really physical space of a data center, right? And this is something where, of course, now lots of these aspects are growing in complexity as we have more GPUs, not only CPUs anymore, different types of GPUs, which may be important for our AI, right? We need sometimes maybe cutting edge chips versus, sometimes just number crunches for clusters instead of cutting edge GPUs and so on and so on. So there's software enabling this. So for instance, a VMware XT service here, this is something also that you could look up. It just shows you that, of course, the commercial players and the industry is aware that, there's something more than a laptop. And this is already a scale which is larger. So really servers with virtualized software. And many people have this in production. So just that you see, that is also considered already a cloud infrastructure, mostly inside these kind of different, let's say, providers. And if you go then on a bigger scale, really, with VMware, vSphere, and they have vCenter suites and a lot of things which cannot go into all the detail because this will fill, not one lecture, but many lectures. They have lots of functionalities today. Just that you understand in the idea of cloud computing, and the idea of really operating these kind of clouds, and we still have to talk about private clouds, public clouds, hybrid clouds later in the course, where it maybe becomes also for a company important to have internally a cloud, and then at some point in time bridging together with MS Azure and AWS, something we called a hybrid cloud. So this will all come later, but this shows you that this is really a hot topic in the commercial domain, not only at large data center scale already at servers, maybe for a company, this might be really relevant to think about virtualization because it increases the utilization and has many other benefits. And a little bit the standardization and so on around it, I will leave you to the video, which is of course also very nice that we can port applications more easily with the VMs and so on. Similar like Docker containers, we will basically learn at the end of the course. So I encourage you to look the video, and we break here for 10 minutes and then come back refreshed for the second part where we look much more in cloud data center design. Talk to you soon.